Unit 16, Acid-Base Equilibria, pages 201 to 208, and this is focused on acid-base strength. The concept of acid or base strength is related to the amount of reaction. The amount of reaction is sometimes referred to as the percent ionization because the products of acid-base reactions are ions. So how much percentage of ions are produced by the reaction of the acid? Percent reaction is equal to percent ionization. The key feature of strong acids and bases is that they completely ionize, or 100% ionize. HCl, or hydrochloric acid, is a strong acid in water because it completely reacts to make ions. There are essentially no reactants left at equilibrium. Reactions that go completely to products have a large equilibrium constant. Equilibrium constants for acids are often written as Ka. So for this example, you have hydrochloric acid and water initially. However, once the reaction is completed, we have 100% ions, all hydroniums and all chloride ions, and nothing left of our original reactants, which should give us a very large Ka value. These are the common strong acids that you absolutely want to have memorized: hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, chloric acid, perchloric acid, and sulfuric acid. Strong bases have a large Kc. For bases, we use a Kb. So equilibrium lies very far on the product side. The amount of reactant left at equilibrium is negligible. So strong bases also completely ionize, or ionize 100%. So common strong bases, and you want to also memorize these, are sodium hydroxide, potassium hydroxide, calcium hydroxide, the oxide ion, the hydride ion, and the nitride ion. All of these will completely ionize to form 100% hydroxide ions and cations. For bases, you have to pay attention to the stoichiometry. So a calcium hydroxide solid, when placed in water, completely dissociates, but we end up with a 1:2 ratio of calciums to hydroxide ions. For oxide, when you place it in water, you're going to end up with HO here, and then OH here. So basically 2 hydroxides are produced from this reaction. Hydride plus water, you're going to transfer a hydrogen over from the water, and you're going to end up with hydrogen gas, and we're going to be left with a hydroxide. And finally, we're going to move a hydrogen over from the water to the nitride, and that's going to give us NH3, and we're going to end up with 3 hydroxides as a result. So 3 hydrogens are going to transfer from these 3 waters, giving us NH3, and then we'll have 3 hydroxides afterwards. Weak acids only partially dissociate into ions at equilibrium. Most of the acid stays in the undissociated reactant form. HF is a weak acid because only a few percent of the HF molecules dissociate into ions. So if we look at this depiction here, you have hydrofluoric acid placed in water, and it's going to form fluoride and hydronium ions. However, we're only going to partially make some percentage of these, but mostly we're going to retain the original reactants. So when you put HF in water, we end up with mostly HF still, the water is understood, and then we just have a partial ionization of the ions, and so we have a little bit of fluoride and hydronium ions. This is going to result in a small K value for equilibrium. To identify weak acids or bases, check to see if it is listed in the table of strong acids or bases on page 202. If it is not listed, you can assume the compound is a weak acid or base. Strengths of conjugates. Recall that acids and bases create products that are also acids and bases. The products are called conjugates. Consider the strong acid, HCl, or hydrochloric acid, that completely dissociates into ions. So here's the strong acid, and you're going to get 100% hydrogen ions and chloride ions. The conjugate base, Cl-, is a negligibly weak base that will not react in any appreciable amount. So because this is a strong acid, its conjugate is a weak base. The weak acid, hydrofluoric acid, only dissociates a little to create a few product ions. The conjugate base, F-, is also a weak base that reacts to a small extent to remake the reactant HF. So here's hydrofluoric acid, and if only 8% reaction occurs, then we get very little of these products. And so you have a weak acid, and its conjugate is going to be a weak base. Here, HSO3- is a very weak acid with only 0.008% dissociation. And so the reverse reaction actually occurs more to a higher percentage than the forward reaction. And so that means that this very weak acid has a conjugate that is a weak base. The conjugate base, SO3-, is a weak base that reacts to a large extent. Comparing the three figures, we can make these conclusions. The stronger the acid, the more it dissociates into ions. The stronger the acid is, the weaker the conjugate base. The weaker the acid, the less it dissociates into ions. The weaker the acid, the stronger its conjugate base. Examples of strengths of conjugate bases. NO3- is not basic at all because nitric acid is a very strong acid. So, strong acid, its conjugate is a negligibly weak conjugate base. CO3-2- or carbonate is a mildly weak base because HCO3- is a weak acid. Remember, the stronger the acid, the weaker the conjugate base. The stronger the base, the weaker the conjugate acid. Auto-ionization of water. Water dissociates spontaneously. This reaction is called the auto-ionization of water, where you have a water and it ionizes into hydrogen and hydroxide ions, but only a very tiny amount. Note it's in equilibrium. So here, the equilibrium constant K is equal to the hydronium times the hydroxide. Water is a liquid, so it doesn't even count in the equilibrium. And these have an equilibrium constant of 1 times 10 to the negative 14. You're going to want to memorize this. It's a very tiny number, which lets you know that this almost entirely lies as reactants, and we have a very small amount of the ions as product. Recall from chapter 15 that when KEQ is very small, the equilibrium mixture will contain only a tiny amount of product. So when comparing hydrogen to hydroxide, if they are equal in a solution, then you have a neutral solution, the normal case for water. If you have an acidic solution, then you should have more hydrogen ions than you do hydroxide ions because an acid has been added to the water. And if you have a basic solution, you should expect to have more hydroxide ions than you do hydrogen ions because a base was added to the water. So the pH scale. pH is a base 10 log scale used to express the concentrations of hydrogen and hydroxide. Here are the relationships. If you take the negative log of the hydrogen concentration, then you would get the pH. Same thing as if you take the negative log of the hydroxide concentration, you get a pOH. If you take the pH and you do 10 to the negative pH, then you would know the hydrogen concentration. And if you take 10 to the negative pOH, you would find the hydroxide concentration. These equations use base 10 logarithms. You want to make sure you can do these in your calculator. So if I have this hydrogen concentration, then I want to be able to type in negative log 3.4 negative log 3.47 times 10 to the negative 3, close parentheses, and that's going to give me a pH of 2.46. Note because there are because there are 3 sig figs here, there should be 3 decimal places total here on my answers. So it should be 2.460 to be more accurate. Here, I'm going to take the negative log of 6.93 times 10 to the negative 12, and that's going to give me a pH of 11.159. Because this has 3 sig figs, this should have 3 decimal places, and that's how far you round for sig figs with pH. So note 3 sig figs requires 3 decimal places in the pH. If you're working backwards, you should be able to type these in your calculator as well. So to find the pH, if the pH is 2.46, then I want to take 10 to the, raise it to the negative pH, and when I hit equals, then I'm going to get the concentration of hydrogen ions in the solution. Same thing here is if I take 10 and raise it to the negative 11.159, then I get the original concentration of the hydrogen ions that we calculated before. pKa and pKb is when we take the negative log of the equilibrium constant, then we can get, so negative log of Ka is going to give us a pKa. negative log of Kb would give us a pKb, and then you do the reverse. To get the Ka, you take 10 to the negative pKa, and to get the Kb, you take 10 to the negative pKb. Hydrogen and hydroxide, when you multiply them, you should get 1 times 10 to the negative 14 at room temperature in water. And if you wanted to get the pKw, then we would take the negative log of this value, and that would give us 14, which means the pH plus the pOH should equal 14. A weak acid with Ka 1.8 times 10 to the negative 5 would have a pKa of negative log of 1.8 times 10 to the negative 5, which equals 4.74. Given a pKa equal to 4.74, the value of the Ka would be 10 to the negative 4.74, which gets us back to 1.8 times 10 to the negative 5. pH in everyday life, hydrogen ion concentrations typically range from 10 to the 0 to 10 to the negative 14 molar, corresponding to pH values of 0 to 14. Some modern acids create such hydrogen concentrations that the pH is negative. A hydrogen ion concentration of 1.7 molar would have a pH of negative log of 1.7, which is negative 0.23. This figure shows where some common solutions fall on the pH scale. Lemon juice, soda, rain, neutral, detergents are basic, oven cleaners are also basic. Now pause the video and jot down some notes on this note card. Percent ionization is going to be equal to the strength of your acid or your base. Strong acids will yield 100% hydrogen ions, and you have a large Ka value. These are the strong acids that you should memorize. Strong bases will yield 100% hydroxide ions and have a large Kb, and these are strong bases you should memorize. Memorize the strong acids and strong bases above. Weak acids and bases will partially ionize. Strong acids have a negligibly weak conjugate base. Strong bases have a negligibly weak conjugate acid. The stronger the acid, the weaker the conjugate base, and the weaker the acid, the stronger the conjugate base. The autoionization of water yields hydrogen and hydroxide, and when you take that equilibrium expression, it should be equal to 1 times 10 to the negative 14 if you're at 298 Kelvin. Comparing hydrogen to hydroxide, it's acidic when you have more hydrogen than you do hydroxide, it's neutral when they're equal, and it's basic if you have less hydrogen than you do hydroxide. Pause the video, and here's one more note card for this lesson. If you take the negative log of the hydrogen concentration, you get the pH, negative log of hydroxide, you get pOH. 10 to the negative pH gets you hydrogen, and 10 to the negative pOH gets you hydroxide. pH and pOH together should equal 14. Hydrogen times hydroxide should equal the Kw, 1 times 10 to the negative 14. If you are concentrating on sig figs, 3 sig figs should be equal to 3 decimal places of the pH. And then pKa, which is similar to pH in a way, is equal to the negative log of the Ka. Negative log of the Kb gets you the pKb, and then you can do the reverse, 10 to the negative pKa and 10 to the negative pKb for the Ka and the Kb. Same thing goes here. pKa plus pKb should equal 14. Ka times Kb should be equal to 1 times 10 to the negative 14.